We solved your very first syncly linked list problem, which is to count the number of nodes in the list. I hope it wasn't too bad, and now you got a better feel about how algorithms should really be looking like, and also how to trace them on a syncly linked list. And let's now consider a very similar problem, but it does require a little bit of extra complication about reference aliasing. So I'll let you do that quickly, but still do some complete tracing together with you, not just on the paper, but also on the Eclipse debugger. I think both should be beneficial for your learning. Let's now do it. Right, the problem is we want to retrieve the tail, right? Of course, they should be only retrieved without the ed. I'll fix it, right, when you download the slides. We want to retrieve the tail, i.e. the last node in a syncly linked list. It will be a very similar loop that you will have to write, similar to what you had to do in the case of getting the size of the list. You can think about why. But I can say, okay, let's now give you some hints, and then I'll let you pause the video and sketch your solution on the paper. Well, similar hints, the same hints basically. If you really want to get to the last node, you want to find out that node which has a null next reference. That will be the last node. There's no other node in the chain of nodes that will have their next reference being null, except for the last node. That's really the axiom or the property of the syncly linked list or doubly linked list you can always think about. Alright, so now I can also assume that the method is going to go into the syncly linked list class, as you can see also in the source code I made available to you. You can now pause the video and sketch your solution. Alright, so let's now compare your solution with mine. And first of all, it's going to be, again, it's going to be a public method, and it's going to be an accessor method returning the node, right? Since we are getting the tail. So that's why it's returning node rather than integer. The type here is also very important. Do we need any extra input parameter to help us on the computation? No, because using the head internal to the syncly linked list, we will be able to find out that particular node with the null next reference. That's the idea. Alright, so without showing you the code, well, actually I should show you the code. Let's now move on to the paper over here. And let's now try to consider two cases. As I said earlier, one is about empty list, the other one is about the non-empty list. So case number one will be the empty list. We want to make sure your algorithm will actually work at least on these two cases. There might be others in some other operation, but for this get-tail, it should be enough. And number two, it will be the non-empty case, the non-empty list. Right, as I said, when you go through the coding interview, not only that they might just ask you to program the algorithm, the solution on the whiteboard, possibly, they might also want you to justify the correctness of your algorithm. And sometimes justification may not have to be formal. Maybe it's only just about to supply some convincing number of test cases that will cover all the scenario. In that case, I think giving a case for empty list and giving one case, the other case for non-empty list, that should be sufficient, at least for the simple operation like this. All right, so let's now highlight it. All right, so these are the two cases. All right, and case number one, empty list. So it's going to be, again, the empty list should be visualized as the head is really pointing to just the null. All right, so that will be the empty case. Is this working? Let's see. So the get-tail is actually going to declare some current node. We talked about the current, the row for the current already, right? So now in this case, the current is simply going to point to the head in the beginning. Right, so let's now, the first line over here, the current is simply pointing to the head. Basically, the current is also going to point to the null, right, to begin with. And then we're also going to get another node over here, and I want you to compare this local variable over here together with what we used for the get size. In this case, for the get size, the local variable is of type integer, because eventually we want to return integer size. But in this case, we want to return some the tail node. That's why the local variable is of a different type. That's something I want you to pay attention to. Right? So how do we visualize this line? So it's going to be a node, but it's going to be a reference to some node. So the tail will also be pointing to null. Right? That's specifically should be null. So you can think about, let me just go another color over here. So the tail is also going to point to null over here. All right, and let's now try to evaluate the Boolean condition over here. So current, which is null, over here, not equal to null. Null not equal to null is going to be false, right? So that means we're not going to execute the body of the loop, not even for the first time. And then we're going to return the tail right away. And what's the value for the tail? The tail is simply just this. And indeed, you know what? This is really corresponding to, let me just refer you to that earlier notes. Remember when we talk about the intuition of the linked list. If you look at that, we'll talk about how do you really visualize an empty singly linked list. It's actually when the head and tail are both null. So it's really corresponding to what we said earlier about intuition. So what you may want to do is to really make sure you understand everything I said over there earlier about intuition. There are many hints about how algorithm can be implemented on a singly linked list. All right, enough connection. Let me now go back to the getTail algorithm over here. All right, so the empty list is indeed working. So check. Let's now talk about the non-empty list case over here. And we're going to use this the same list over here just for simplicity, so you're already familiar with it. Let's now go line by line. So for line number 2, we're going to initialize the current to be the head. So where is the head at the moment? Well, for the list, you can see the head is pointing to the Allen node over here. And so we're going to initialize the current to be just pointing to the same object as the head does. Right, so current is actually going to point to just the Allen node. So current should be Allen in the beginning. And also we're going to have this extra local variable reference, right, kind of analogous to the size local variable as we did in the previous method. And tail will just be initialized to null. So let me put it here. So tail initially would just be pointing to null, but we can definitely expect to update it very soon. And we're going to evaluate, so let me just make sure. So this line is done. And also we're going to execute line number 4, and we're going to compare this Boolean condition. What is current? Current is pointing to this node, Allen node, which is not null. So not equal to null should be true. So that will be true, meaning that we're going to go for the very first iteration, right? So when we go for the first iteration, we're going to, first of all, update the tail to be the current, right? Notice that we say tail is assigned to current, right? So tail is going to point to wherever current is pointing to. Current is pointing to over here, and tail, rather than pointing to here, is actually going to point to the same node, right? Let me put it this way so we don't really get messy, right? Tail is not pointing to here anymore. Instead, tail is now going to be aliased to the same object as current. And then we're going to go for the next line, and this part over here, current is assigned to current.getNext is very important. One exercise you may want to do is to hypothetically get rid of this line and think to yourself what's going to happen. My short answer would be it's going to become an infinite loop, because you will never get this condition to really evaluate to false. In that case, you will never exit from the loop. That'll be some quick remark. You may want to take the notes and then give a try on your own. Right? Make sure you understand that. Right? Let me now do the updates. So current is simply assigned to current.getNext. So current.getNext is pointing to here. So that means current is now going to point to the node to the right over here. Right? Exactly the same procedure as we did. So now we are reaching the end of the first iteration. And what will be the ending at this point? What's the reference for tail? Tail is here, just one behind the current, right? That's just the way it is, right? So tail is really pointing to the Allen node. All right, so tail is really pointing to the Allen node. All right, that's good. And then we're gonna go to the header for the while loop for this second time, right? Look at the blue ones, right? So by the way, the pink one, don't get confused. That's for the empty list case. So I'm going to evaluate this. What's current not equal to null? Current is pointing to the mark node at the moment. Let me just put it down. It's now pointing to the mark node, right? At this point. And then mark not equal to null, indeed, true. Meaning that we're going to go for the second iteration. And we're going to go into it and then execute those two lines again. And we're going to update the tail to let it catch up with the current. So tail is going to be assigned to wherever current is pointing to. So tail, rather than pointing to over here, so tail is now going to catch up and then point to the same node as the current. And we're gonna update the current so that it will stay one node ahead of the tail again, right? So current is gonna point to wherever whatever its next is. So current.getNext is pointing to this node over here. So current, rather than pointing to there, is gonna be pointing to over here, the Tom node over here. So at the end of the second iteration, what is the tail? The tail will be pointing to the mark node. So let me put it here. So it should be mark over here. I might be able to write just a bit better. All right, that's a mark. And so now we're going to evaluate the. So now we are done. We're going back to evaluating the while loop header again, right? The third time. And at the moment, what's current? Current is pointing to the Tom node. All right. And when we evaluate current, which is Tom, is not equal to null, should be also true. So we're going to execute the third iteration, which is not surprising. And then, so now for the third iteration, we're going to execute these two lines. Let's see what's going to happen. So when you execute line number 5, tail is going to catch up. It's going to be reassigned to current. So tail, rather than pointing to over here, is now going to point to wherever current is pointing to. Now you can see really the pattern of how the current and tail should be updated, right? Kind of rely on each other somehow. And we're going to also updates. We're going to execute line number 6 as well to update the current. So when you update the current, it's assigned to get current.getNext. So current.getNext, current is pointing to over here, .getNext is pointing to null, right? And we're going to make sure current is reassigned to null. So current, rather than pointing to this node, is now going to point to this null reference. Okay. Current. And then we are done with the third iteration. And let's put it down. So now we are done with the third iteration. And what is the reference for tail over here? Right? You can see tail is now pointing to the Tom node. Tail is actually pointing to the Tom node over here, which makes sense. So that should be the ultimate answer to return. But let's see if that's really the case. So that'll be the Tom node. So now we are done with the third iteration. So now we're going to go back to evaluating the header of the loop for the fourth time, right? So I'm going to put an arrow over here, the fourth time. And what's current? Current is actually null at the moment, right? Let's put it down first, and we're going to evaluate. So current is actually null. So null, not equal to null, itself is going to be false. And so that's why we're going to put false over here. In which case, we're going to bypass the body of the loop, and we're done. So there are only 3 iterations required. And then we're going to return the tail. And when you return the tail, what's going to happen? What's tail? Well, exactly the last node over here, right? So that's really something you will have to also do by yourself to make sure you can really see how the current can, first of all, get ahead and also be caught off by the tail, right? And so eventually, tail will be really pointing to the last node, for which the next reference is really the null reference. That's something you want to convince yourself. All right, that's about the paper tracing. Let me talk a little bit about the running time. The running time arguments will be very similar to what we did earlier for the get size. In some way, the tail over here, that's the extra complication, is not really the key thing for you to actually focus on. It's mainly about how many get next that you will actually have to write, you will have to run in order to get to the end, right? So the critical question will be how many iterations, each iteration is gonna call a single time for the get next before hitting a null reference, right? So you can see that'll be the first one, second one, and the third one, exactly equal to the number of nodes that's in the chain of nodes. So that's why it's linear. All right, that's very similar arguments as we actually set for the get size method. So it's also going to be linear. Okay, So for this kind of algorithm, when you actually got a loop, and every time you're trying to update the current using the get next, so all you got to think about is how many get next, in the worst case, do you have to really invoke in order to reach to the condition that will make the this Boolean condition false, so you will exit from the loop. That's really the insight. Let's now go back to the slides and then see what else. So that's the code that we just gone over. You want to make sure you really understand the difference and similarity. Compare this with the get size method. And the same question here about when the loop will actually exit. And what's the running time? Well, as we discussed, it should be linear time. And let's now talk about the counterparts method in the array. How do you really get to the tail of the array? Well, basically, how do you get to the last element in the array? Does it require linear time? Well, it turns out no, because all you got to do is go for array indexing, and this is simply some simple arithmetic. It's also constant. Overall, it's going to be just constant, right? So you can see to really get the size or to really get to the last node, in the case of a singly linked list, when you only got the help of the head reference, in that case, it's going to be linear time as opposed to constant time in the case of the array. And I got one more slide to show just to see if we can really do better than linear time. We definitely can, but before I get there, I would like to switch to Eclipse very quickly, just to show you how you may trace the get tail method. All right, just to show to you. All right, and at the moment I don't really have in my test cases, you can see the test string singly linked list. I don't really have that method being called, but I can just add one very quickly. I think it's rather important for you to see how you can trace it. Let's say I got this one corresponding to approach number one. Approach number one, maybe not. Let me just go to this one. How about that? If you look at the test singly linked list 01, right? This might be the one we traced before. I forgot. Anyway. Let's say this one here. So this is after let's say after we set up the list, we also want to see what the tail is. Okay, so we can say assert true, or we can say assert true is fine. Okay, so what should be the tail? So the tail should be the tom node, right? So tom should be equal to list.get tail. Okay, it seems like I don't have that particular method. Okay, so maybe what I should do is I should really go back to my singly linked list over here, and then let me see. I should really get a tail. Yes, but it should be public. My bad. All right, let me fix it. Right, it should be public. All right, let me go back here, and all right, good. And I just want to trace this particular assertion over here just to make sure you know how to trace it. Right, so I'll put a breakpoint. Let me remove the earlier ones. Remove this. Remove this. I will go directly to line number 67 in my case. So right before we try to invoke list.getTail. Another way to write this, I'll write it down just for your reference. I can say assert same over here, meaning that the two arguments over here should have the same reference. You can say tom and also list.getTail. They mean exactly the same thing. All right. There's also some basics which I assume you know from 2030, the advanced OOP course. All right. Let's now try to trace it quickly. And I'm going to right click on the JUnit test class, and then I'm going to say debug as JUnit test. And then switch to debug perspective over here. And then now I'm here right before executing list.getTail, right? If you look at the list over here, if you expand it, you can see we got, don't worry about the size and tail attributes. So these are the improvement which I would suggest in the next slide. So in the source code, it's already being implemented. So let's pretend these two attributes are not here. Look at the head over here. You can see head is pointing to the Allen node, and the next is pointing to the Mark node, and the next is pointing to the Tom node over here, right? And Tom node is the next will be just the node. That's a chain of nodes. We want to see the get tail. So if you want to see how the method gets executed, you want to say step into. If you hit on step into, so now this will be the get tail, right? I'm not going to really go iteration by iteration in some way. I just want to show you this. Go to expressions over here, and let me remove all the earlier expressions. This is what you should do to really practice yourself how to use debugger. I'm going to put the critical variables over here. I want to see current. I want to see, at the moment, we haven't declared current just yet, so that's why it says error. Okay. And also, we're going to see what the tail is. And also, we're going to see what the pretty much corresponding to my tracing table. And also current not equal to null tells us whether or not we should really go into the loop, right? Let's now take a look quickly. I'm going to say step over. So now I'm going to evaluating this. So I can predict current not equal to null is going to be true, meaning that I'm going to go for the first iteration. At the moment, tell stays null, which is one position behind the current. The current is currently pointing to the first node, which is Allen, right? So remember what we did in the paper, right? Let me do just one iteration with you, okay? If I say step over here, I'm going to let tell catch up. So if I say step over, in that case, you can see both the current Allen and also tell also Allen. More to that, if you try to see current equals tell, also true, right? If you remember in the diagram over here, for the first iteration, what we did was we say current and also tell, they point to the same objects. That's why when you say equal for check to check the reference aliasing, it will be true, right? That's some correspondence you want to make sure you understand. Right, and then we're going to make sure its current stay one position to the right ahead. Right, I'm going to say current is assigned to current.get next. What you can try is this. Before I execute line number 44, I can say current.get next. So the next node, which I haven't said just yet, the next one is going to be Mark. And the current at the moment is actually Allen, right? So after executing this assignment over here, I will see that the current will become actually Mark rather than just Allen. Right? So if I say step over here, in that case, you can see current has become Mark over here. Right? So that's kind of the change on the nodes. You want to make sure you understand exactly what's going on. It corresponds to exactly how I trace on the paper. All right, that's about it. And of course, if you want to just get to the end, you can also do so. Put a breakpoint line number 46 outside the loop, and then you can say step return. And now we can see what the tell is going to be returned. If you look at the tell over here, it's really pointing to the top node, which is the last node. That makes sense. All right. Let's say stop, and then make sure you go back to the Java perspective. All right. Let's now go back to the slide. One more slide to show, just about the conclusion about how we can improve the performance for get size and also get tell. And there's a tracing table that we did all together. You can definitely review it. Let's now talk about one more slide. Can we do better? Right? So in practice, we may frequently need to actually use the get size method or to really use the get tell method. Why? Let's give you some example. We may just want to frequently access the tell of a list. Let's say you may just have a singly linked list representing the service queue. Maybe for Rogers, the telecom company, in which case every time customer actually want to call for help, for technical support, they will join the service queue. They will be added to the end. So that's why the tell will actually be very useful feature to make it efficient. Similarly, we may also want to inquire frequently about the size of a list. Well, let's say also use the service queue example. We want to know what's the current size of the service queue. Maybe when it gets to 100, in that case, maybe we should really block for any further entrance into the queue, just to make sure we actually maintain the quality of service, right? That's another example. So these two methods or these two features should really be supported in an efficient way. So linear time is not the way to go. How can we improve it? And so both it's a linear time, as we said before, because you cannot get away from just starting from the head and keep calling the get next reference until you reach the last node, whose next reference is null. That'll be linear time. And so here is a principle that you will see very often, well, maybe at least a few times in the course. The principle will be, since time is so precious to us, we want to trade the space for that. How do we do that? Well, basically, rather than simply defining get size and get tell as the method which will actually individually require a loop, which will be linear, what we want to do instead is, why don't we simply make the size and the tell both as attribute values? Meaning that if you, given that you will update these two attribute values whenever appropriate, in that case, whenever you want to know the size or the tell of the list, you can simply return the value for those attributes. And returning something is simply constant time. So that'll be the idea, that kind of rationale behind. So what we want to do is we want to declare a new attribute tell, always pointing to the end of the list. Initially, tail and head pointing to both pointing to null for the empty list. And whenever you add a new node, for example, into the list, you want to make sure that new node becomes the new tail of the list. That's something you will also see later when we program other methods. And also for the size, you want to make sure every time if the size should be updated, you should update it. For example, if you want to remove a node from the list, in that case, size should be incremented. If you add a node to somewhere in the middle, the size should also be incremented, right? That's we will see example later. And the running time of returning either the tail or the size will just be constant time, just a single return statement, right? Again, the principle is really called trade the space for time, right? The only catch is you want to make sure for all the methods for the singly linked list, if applicable, you have to make sure you update the tail and the size whenever appropriate. So here's one question just to conclude this part of the lecture. Why don't we simply declare attributes to store references for all the nodes between head and tail? For example, we have a reference called maybe the second node. Well, we already got the head for the first node. Why don't we have second node and also third node, fourth node, and all the way to tail? Can we do that? Is it even possible though? Well, it's not even possible because we don't even know how many nodes there might be in the list. So if you just say I got second, third, fourth, all the way to 100, I can tell you that at the runtime, it's also possible we got another 5 nodes that can be added beyond 100. So it's never possible to really have precise reference for every node in the singly linked list. If you ever try to do that, that means you haven't got correct understanding about the list. Its structure is simply dynamic. You simply cannot predict how many nodes it might appear in between. You just don't know. Alright, so at the time of declaration, we simply do not note how many nodes there will be at the runtime. So you simply just cannot declare like the variables in your singly linked list class to say second node, third node. You simply don't know how many should be included, right? So that's a concluding remark I would like to make. All right, so that's about the second problem of getting the tail of the linked list. So now hopefully you got even better idea about how the linked list operation should work. Just remember, reference aliasing is really your friend about keeping track of where you are, and also maybe have some auxiliary local variable. And from the next problem, we're going to assume we actually got a tail and also size attributes already declared in the singly linked list class. And let me show you quickly, and then we're done for this part. If you go to your singly linked list class, you can see not only that we got head, but also we got 2 other private attributes, tail and size. Remember, we are trading space for time. Alright, that's about it. And let's now take a look at the third problem.